if you want to make a crystalline solid, requires the particles in the solid to organize. So the ability for the particles to organize in 3 dimensions, in rows and columns, or in a cubic shape, or in a hexagonal shape, or rhombic shape, or whatever the shape of the crystal may be, the ability for that to happen, it depends on the strength of the attractions between the particles, because if the particles don't have attractions, or if they have very weak attractions, everything at any temperature has some motion, and if the attractions aren't strong, they're not going to stay in an organized manner. Right? So it's like I put up well, I guess one analogy would be if I have a box and I put in a bunch of Legos and I line them up nice and neat in the box, and then I shake up the box, they're not going to stay organized. Right? So the motion that's present in anything normally causes things to get random and move around. So things will not stay organized in a crystalline arrangement unless the attractions are holding it together. So if I just lay the Legos on top of one another nice and neat and I shake the box, they're all going to be completely randomized. But if I actually attach the Legos together and stick them together, then if I shake it gently, they might actually stay organized because of their attractions and their connections. So what we can say is the stronger the attractions, the more likely it is to be crystalline. And that's why ionic substances are pretty much always crystalline. Because if I have really strong attractions between positives and negatives, that's going to keep that lined up. If I want to break up, if I have this in rows and columns in all 3 dimensions, every negative is fully surrounded by positives, every positive is fully surrounded by negatives. I want to break that up. I have a lot of attractions I got to break. It's going to take a huge amount of force. Just like if the Legos are really, instead of just sticking them together, maybe I put glue in between them. Some super glue, and then I stick them together. There's no way I'm going to break that up by shaking it because the attractions are too strong. So it just stays organized in that case. The other factor that affects the organization is the shape of the particles. And this is a little bit more difficult to visualize. So what we like to say here is if the shape of the particles, if the shape is small and regular, and what I mean by regular is every particle looks the same as the neighboring particle, then even if the attractions are weak, it will probably still organize. And so imagine if I have a box of spaghetti, uncooked. Now you buy the box of spaghetti. It's this long box, and the noodles are all rigid. They're not cooked yet. If you take that box and shake it up, and then you open it, the noodles are still going to be nice, lined up next to one another. They don't even have attractions. I mean, they actually do have attractions because they have friction. So there's the molecules on the surface of the noodles attract the molecules on the surface of the next noodle through London forces or hydrogen bonds. Or it's not that strong, though. So if the shape is regular, like rigid rods or spherical shapes, and it's very easy for them to organize, then their attractions were much more likely to keep them organized. Now, if you take the spaghetti and cook it, and then try to jam it back in the box, it's never going to organize, because every noodle bends in a different direction. And so if you have, so that would be more likely to be crystalline. if you have an irregular shape or very large or long chains of molecules, then it's much more likely to be amorphous. Amorphous. Because there, even if you have strong attractions, if you try to organize a bunch of things that don't look the same as one another, you can't do it. It's like the difference between, if you want to pack a bunch of Legos in a box, it's easy to organize them because they all have a rectangle shape. If you try to pack all of some kid's toys in a box and he has a bunch of action figures and I don't know, what do kids play with now? Whatever they're playing with, and they're all different shapes, you're never going to get them organized. If you have a bunch of iPads, then they're probably easy to organize because they all have the same shape. Right, that's what kids play with, I guess. I was going to say Matchbox cars. Oh, is that something nowadays? Ah, childhood. Does that help answer your question? Other questions? Abraham? Good question. So, if you're talking about lattice energy, you're talking about a crystal. So, what we're talking about here is the energy holding together this crystal. So, lattice energy is usually measured in the quantity of energy, like joules or kilojoules, per mole of the substance. So that means if I have a mole of this crystal, meaning I've got Avogadro's number of these units, that's a whole bunch of units all lined up. The lattice energy would be the energy necessary to break those attractions and allow them to flow around past one another. So if I've got strong attractions here between all these charges, and I've got a mole of those, it's going to take a huge amount of energy to melt it or to break their attractions. So if the particles pack well, and they can get close together, and they can organize in a way to line up the attractions, and if the attractions are large, where you have maybe full charges or some very large partial charge attractions, then it will have a greater lattice energy. So lattice energy is like bond energy. It's not a direct measure of the quantity of potential energy that something has. And I wish we would just pick a way of thinking about energy and stick with it instead of flipping back and forth all the time. Normally think of potential energy. The more potential energy something has, the more unstable it is. The fewer attractions it has, the more potential it has to form some attraction. Lattice energy is not the same as potential energy. So if I say something has a lot of lattice energy, it doesn't have a lot of potential energy. Because lattice energy isn't the energy it has at this moment as a potential to release if it became more stable. Instead, lattice energy is the energy required to break up its stability. So you have to think about it in the reverse sense. If it is stable and the attractions are holding it together strongly, then it's low in potential energy. And it has a lot of lattice energy. Lattice energy isn't something that an object has. It's something that's required for the object to absorb in order to break its attractions. Right? So when we break attractions, it's always endothermic. The substance always has to absorb energy. So if you have a very stable substance with a very low potential energy, because I've got these nice attractions, everything's all lined up, all the attractions are forming, I've got lots of quantities of charge, maybe even a +2 and a -2, or a +3 and a -3, really strong attractions, very stable and low potential energy. That would require a very large lattice energy to make it unstable and break the attractions necessary to allow the particles to become disorganized. So it's the energy required to go from organized to disorganized, and some attractions have to break in that process. Oh, I forgot to answer your question. Oh, carried away there. So with an increased lattice energy, you have a decrease in solubility. And that's because if the lattice energy is very high, or the energy required to break up the attractions is a large quantity of energy, then those attractions are not likely to break. And in order to dissolve it, you have to break those attractions apart so it can get surrounded by solvent molecules. And so it's going to be hard to do that if you have a large lattice energy. So, especially among ionic substances, salts that have full charges attracting, the greater their lattice energy, the less soluble they're going to be.